Bismillahirrahmanirrahim. So let's start our second lecture. So this one will be the article number 2.2, the temperature dependence of resistivity. Okay. So now, so we know that the material it depends on for each material there are some parameters like the resistivity or the conductivity or various things, various parameters are there: electrical, magnetic, optical parameters, and so on. So, we know from our electrical circuit concept or from the very beginning of our physics things, that one is with the increase of the temperature, the resistivity will increase. And we have also learned some formulas from where uh, we can say that that one is RT equals to something like that R naught into 1 plus alpha t, something like this. We have memorized these formulas, and we just put these formulas to find out the temperature dependence resistivity. Now, in this chapter or in this article, article 2.2, we will learn the temperature dependence of the resistivity and this sort of things. So let us assume this one is the two, that means two electrons. That one is this one is the first electron, and this one is the next electron, and there is a corresponding collision in between these two electrons, and the cross sectional area of this electron is S equals to pi a square, where a is the radius of this electron. Now, let's assume the mean free path, that means the path in between these two electron, or the path in between these two electron, is that one is defined as L. That one is defined as L. And if this velocity and the velocity of these two electron, that means the collision velocity in between these two electron is U. So we can find out this mean free path, or this path L equals to U multiplied with tau. So we can write down the formula for the mean free time. Tau should be equals to 1 divided by SUNS, where NS is the concentration of the scattering centers, and the volume is SL. So why SL? S is the surface area and L is the mean free path. So if we multiply the area with the length, then we can find out the volume. So if we consider that one scattering center, that means if this value equals to total value, SU, SU means S is the that means surface area pi a square. U is the velocity in between the two collision electrons. Tau is the what is the tau is the relaxation time. Ns is the concentration of the uh, scattering centers, should be equals to 1. So we can, from this formula we can conclude that the mean free time tau should be equals to 1 divided by SU ns. Now look, the mean speed U of the conduction electron in a metal can be shown only slightly temperature dependent. That means we can find out this U is slightly depends on the temperature. Now we know that this cross sectional area pi a square, this pi a square, if the electron's path crosses the pi a square, it gets scattered. So the mean free path tau is inversely proportional to the cross sectional area pi a square. So from here we can write down that tau should be equals to 1. In place of s we can write down pi a square, then U n s. So we can write down from here that tau is inversely proportional to the pi a square. Tau is inversely proportional to 1 divided by, or tau is inversely proportional to pi a square. So we know that from the from angular motions things, that the average kinetic energy of the oscillation is 1 by 4 m a square omega square, where omega is the oscillation frequency. So similarly we can write down that 1 by 4 m a square omega square equals to half kt. So if we look this mass, this two portion is a constant, m is a constant, half k is a constant, and omega is constant. So a square, this a square is proportional to temperature T. So this a square is proportional to T. So we can write down this tau. Tau is proportional to 1 divided by pi a square, or if that a square is proportional to t, then we can write down that tau is proportional to 1 by t, or we can write down tau equals to c divided by t, where c is the temperature independent constant. I think this one is clear. Now we know that the relationship between mu t equals to e tau divided by me. So mu d equals to, so we can put down the value of mu d, tau by ct. So mu d should be equals to ec divided by mt. Is that clear? Okay. So this one is the mobility. So we have find out that this sigma or tau is inverse proportional to the time, sorry, temperature. So the resistivity of the metal rho of T equals to 1 divided by sigma T, because the conductivity is the inversely proportional to its resistivity, or the reciprocal of resistivity is known as conductivity, or the reciprocal of the conductivity is known as resistivity, and so sigma T, we can replace this sigma T value by 1 divided by E n mu T. From our last lecture, we have learned that sigma t equals to E n mu d. Now, if we put the value of mu d here, then put the value of mu d here. So here we see that this total portion is a constant terms. This total portion is a constant term. So the rho of T is directly proportional to temperature, and the sigma of T, or the conductivity, is inversely proportional to the temperature. So this can be written as rho of t equals to A of t, or rho of t, that means the resistivity of the material is directly proportional to the temperature. Similarly, we can write down that sigma of t, that means the conductivity of the material, is inversely proportional to the temperature. So this one is the relationship between the temperature with respect to or the temperature dependence resistance. Now, same way, try to solve the example 2.5, temperature dependence of the resistivity. So, as because this writer is from Canada, so here he shows the values of Saskatchewan in the summer to winter. So in the summer, the temperature is 20 degrees Celsius, and in the winter, their temperature is almost minus 30 degrees Celsius. So using that formula, you have to find out the, so what is the percentage of change of the resistance with the pure metal or from Saskatchewan summer to winter. Neglect the changes in the dimension of the wire. That means no need to consider about the dimension of the wire. Just consider the temperature with the resistance. So we know that they are linearly proportional. So Easily you can find out the percentage here. So try to solve 2.5. Next example 2.6. Drift mobility and resistivity due to the lattice vibrations. So given that the mean speed of the conduction electron is 1.5 into 10 to the power 6 meter per second, the frequency of the vibration of the copper atoms at room temperature is 4 into 10 to the power 12 per second. Estimate the drift mobility. Estimate the drift mobility. What is drift mobility? Mu d of the electrons and the conductivity of the copper. Conductivity means sigma. The density D of the copper is 8.96 gram per centimeter cube, and the atomic mass is Ma is 63.56 gram per mole. So this one is for the copper ion. So same way, just using the same formula, you can solve this math. So try to solve this math, and if you face problem, we can discuss these things in the problem solving class. Now this will be the end of your article number 2.2. Now, and the article number 2.3. 2.3, that one is the Matheson's rules. So we will not go with the uh, Nordium's rules. Only follow the Matheson's rules. So because the only this one is included in our syllabus, and this one is not included in the syllabus. Okay, so Matheson's rules and the temperature coefficient of the resistivity. That one is article number 2.3.1. Look, the theory of the conduction that considers scattering from the lattice vibration only works well with the pure metals. Unfortunately, it fails for the metallic alloy. Now, look, so we know that from the definitions of potential energy, PA, potential energy, that means that one is the work done. So if we take the differentiation of this potential energy with respect to dx, that means that one will give us the force, because we know that force multiplied with the displacement, force multiplied with the displacement will give us the work done, and the ability to do the work is known as energy. So if you look at this figure 2.6, then you see that there are different types of scattering process. So that means one electron is moving one direction, another electron is moving another direction, and so on. So they're trying to find out the scattering force. So this scattering force can be find out using the derivative by using the derivative of potential energy. Now look, so if we check, so if you can check from here, in general an electron may be scattered by both the process. Electron may be scattered by both the process. So the effective mean free time tau between two scattering event will be less, and individual scattering time tau t and tau I. Okay, so what is tau t? The effective two types of mean between the collision is one tau t for scattering time from thermal vibration. Tau t is known as thermal vibration, and tau I is the impurities only. That means this mean free time is for the thermal vibration, that one is defined by tau t, and for the impurities material, that one is denoted by tau I. So the total, or the total mean free path for an impure material can be 1 divided by tau equals to 1 divided by tau t plus 1 divided by tau I, where tau t is the, in case of thermal, uh, in case of thermal is in case of thermal vibrations, and tau I is for the impurities. Now, if we check the relationship between these time collisions with the mobility, then we can simplify these things. 1 divided by mu d should be equals to 1 divided by mu l plus 1 divided by mu I, where L is the lattice scattering limited for drift mobility, and mu I is the mu impurity scattering limited drift mobility. So mu L should be equals to same formula, E tau T divided by M E, and mu I equals to E tau I divided by M E. Now we know that from the resistivity formula, we know that rho equals to 1 divided by E and mu d. Now put the value mu d, then rho equals to 1 divided by E and mu L plus 1 divided by E and mu I. Same way. So what we can write down, rho should be equals to rho t plus rho I, where rho t equals to this one and rho I equals to 1 divided by E n mu I. Now the here what we can find out that the resistivity is, we know that resistivity is directly proportional to the temperature. So tau t, or this time temperature dependent relaxation time tau t, should be inversely proportional to temperature. Now if we look from here, the mean time tau I between the scattering events involving electron collisions with impurity atoms depends on the separation between the impurity atoms and the concentration of those atoms. If Li Li is the mean separation between the impurities, then the mean free time between these two collision impurities along with this equals to Li divided by U. How this one is Li divided by 2 U? We know that U equals to, that means the velocity U equals to L divided by T. So what will be the mean time? T equals to L divided by U. I think this one is clear. Now the summation of the rules of the resistivity from different scattering mechanism is that one is shown in equation number 2.15. That means rho resistivity rho equals to rho t plus rho I. This one is known as Mason's rules. So this one is known as Mason's rules. So rho t should be equals to rho equals to rho t plus rho r, where rho r is the known as residual resistivity, and this one is due to the scattering of the electrons by impurities. So we know that the temperature dependence rho is we found rho equals to at, that means that one is linearly proportions, but here in case of impurities materials, then rho should be equals to at plus b. There is another constant terms, proportional constant terms. So that one is not a linear passing through origin. That one is there is a slope a with this temperature. Now the temperature coefficient of the resistivity TCR, the temperature coefficient of the resistivity TCR alpha naught is defined as a function of the change of the resistivity per unit temperature and increase at the reference temperature T naught. So alpha naught should be equals to 1 divided by rho naught, then delta rho divided by delta t at the time t equals to t naught. So the formula for these things, resistivity rho should be equals to rho naught 1 plus alpha naught t minus t naught. This alpha naught is known as temperature coefficient of the resistivity, or in short, that one is known as TCR. And you will find that there are some approximations, or there are some in details of different materials are there. So if now you will find a chart for different materials. So if in the exam, if I give you something, if that one is a physical exam, then I will, if I ask you to find out uh, these values, then I will provide you with the chart. Now, the resistivity versus temperature behavior of pure metal can be empirically represented by a power line. That means rho equals to rho naught T divided by T naught with the power n. So this one is the formula for resistivity of pure metals. Okay, so you will find a chart for temperature with respect to the resistivity. Now, using the Matheson's rules, you have to solve the example 2.7. Explain the typical resistivity versus temperature behavior of an annealed and cold walled copper containing various amounts of nickel as shown in figure. So, annealed means at high temperature. Whenever we use high temperature, then the properties or the lattice constant, or there will be some changes of the internal properties of this material. That means annealed means the material, or the characterization of that material at high temperature, and the cold word means that uh, characterization of that materials in a very low temperature. And they are asked for the various amounts of nickel here. So next, in the example number 2.8, that one is maybe for a pure metal, the temperature coefficient of resistivity alpha and the resistivity index n. If alpha naught is the temperature coefficient of the resistivity, that means TCR at temperature T naught, and the resistivity, obviously the equation rho equals to rho naught T divided by T naught power n. Show that alpha naught equals to n divided by T naught T by T naught to the power n minus 1. Okay, and you have to comment about your conclusions, and try to, and after that they have given all the values, and try to find out this alpha naught. So try to solve example 2.8, and if you face problem, we can solve these things in the problem solving class. Similarly, try to solve example 2.9. T set a different resistive temperature. If alpha 1 is the temperature coefficient of resistivity TCR at temperature T1, and alpha naught is the TCR at T naught, show that alpha 1 equals to alpha naught divided by 1 plus alpha naught T1 minus T naught. And similarly, try to solve the example 2.10. That one is given for a fluorescent bulb. So your syllabus of this first chapter, that means in this second chapter, will be up to 2.3.1. So if we look at this syllabus, then first of all you will say the classical theory of electrical and thermal conduction. That means scattering, mobility, resistivity, temperature dependence of the metal resistivity, Maxim's rules, and the last one is left. That one is thermal conductivity. So this one will be the end of our second lecture, and in the last lecture we will learn about the thermal conductivity. So that one will be the start of the third lecture. So try to go through up to this, and if you face any problem, we can discuss these things in the problem solving class. Okay, thank you.